Hey, everybody on Zoom. Hopefully you'll be able to see what I'm writing okay. Okay, so my talk is accelerating solitons. This is based on two papers that are out, and those are with Ilarion Melnikov, also a former Aggie, and andCostis Papageorgakis. And also, I'll talk a little bit about work in progress with those two gentlemen and one of my colleagues at Penn State Fayette and a student, Quentin Hales. So the outline, I'll start with motivation, and then I will talk about the forced soliton equation, which is the equation that describes solitons undergoing acceleration and the radiation that they produce. And then we'll talk a little bit about how that equation might be used to compute semiclassical soliton form factors away from the usual adiabatic regime at arbitrary momentum transfers. Okay, so let me start with the motivation by way of a question. Oh man, this chalk is breaking. Okay, QFT. Okay, so consider QFT on good old Minkowski space. For the moment, we'll be in general dimension. Let's suppose we have a coupling, I'll call little g, and let's suppose that this theory admits topological solitons. So for example, monopoles, vortices, kinks. So in this theory, let me just introduce a tiny bit of notation. So first of all, we have perturbative particle states, one particle states, which I'll denote by capital psi sub k. I'm going to use this funny double bracket notation for states in the Hilbert space of the QFT. Those guys we can think of as being created by the basic field operator in the theory, or more precisely, the creation mode inside the field operator. So, yes, because if we're going to think of these as asymptotic particle states. Yeah. Yes.
In the first line, you said you're topological soliton.
Yes.
Why suddenly switch to perturbative? Given that
Just hang in there. Okay. I need to talk about these guys, and I need to talk about solitons. So we also have soliton states, which are also one particle states, labeled by a momentum, and possibly other things. So the momentum for the solitons, I'll use a capital letter. Let's draw the propagator for the perturbative particle with a solid line, the propagator for a soliton with a double line. Okay, so here's the first version of the question. And this is a question that I've been thinking about for almost 10 years now. I still don't know the answer. Should we allow virtual soliton, anti-soliton? So let's denote that SS bar. Pairs to run in loops. One considering, and people have heard me talk about this before. I've been, as I said, I've been asking this question for a while. Hopefully we've got some new developments today. So should we allow virtual soliton, anti-soliton pairs to run in loops? One considering quantum corrections. To perturbative processes. In other words, processes with only perturbative particles in the external states. So the simplest thing you can imagine is a soliton, anti-soliton loop correcting the perturbative particle propagator. So S bar. Okay, so that's the question, one version of the question. So naively, the answer is yes. Why? Unitary. Soliton anti-soliton state is a state in the Fock space, the multi-particle Fock space, because the soliton is a one-particle state.
Is there any textbook description of solitons interacting with perturbative states like this diagram seems to suggest?
No. There are a few papers. I've never seen it.
Which are the magic papers we should benefit from?
So there are discussions trying to think about this as a sort of a coherent state of particles. Druckier and Newsonov. Druckier and Newsonov from the late 80s or early 90s. It's one of the ones that's the most cited.
Another one?
There's really very few that talk about this.
Have you in your paper given a pedagogical description of this?
Yeah, so this is the big paper, and then any paper that's relevant that I'm not thinking of right now, reference to there. But Druckier.
So you explain the formulas and how you treat solitons interacting.
Yes, yeah, we're gonna.
Okay, thank you.
We're gonna go. Here's what we're gonna do today. Part of what we're gonna do. Now, less naively, you might say no, because such contribution should be beyond the applicability of perturbation theory. So this question is probing non-perturbative structure in QFT. Now, and that idea again comes from the coherent state picture, where you would say that the difference between the soliton anti-soliton pair and some linear combination of perturbative particles with varying amounts of them, you can't see the difference between that until you get to non-perturbative order in perturbation theory. So another way to phrase the question then is, what is the leading contribution? So let me put this down here. So version 2. What is the leading contribution? In G, our perturbation expansion parameter of S bar pairs to perturbative processes. Is it exponentially small? And if so, can you compute the coefficient, the leading coefficient? So that's a hard question. But one idea to try to address it, which has been around for a long time, is to rephrase the question using crossing symmetry of the QFT. Okay, so old idea. By crossing. Okay, so what does that mean? So the process where we have a perturbative particle coming in and pair creating a soliton anti-soliton. Let me give that soliton momentum PF, the anti-soliton. Let me call this momentum minus PI just for convenience. That's equal in the sense of amplitudes by crossing symmetry to the process where the perturbative particle comes in and it is absorbed by a soliton with momentum PI, and then the soliton goes out with momentum PF. And in terms of amplitude, the way we would write this is K for K to minus PI bar PF is the same as the amplitude for K and PI. Now let me remind you how that amplitude appears in something that looks like something we might try to compute. So it is the coefficient essentially of the momentum conserving delta function in the matrix, in a certain matrix element. So I've got a delta function k plus pi minus pf times this amplitude. And that's equal to the Fourier transform of what's called a Solitons form factor. So integrate over space time x, e to the I k dot x times the following matrix element in the QFT. So remember, phi is the field that creates the perturbative particle. And then here we've got initial and final Soliton states.
So this is an equation for the vertex.
Yeah. That's right. So this is off shell. The Ki and the Kf can be taken on shell, but the K is whatever it is by momentum conservation. Okay, but this would be a building block then for that thing. Now, yeah. So this thing, or this whole thing actually, is what's called a Soliton form factor.
Let's see why this is a crossing symmetry. In what sense is crossing symmetry?
Well, crossing symmetry is the usual symmetry of QFT under if you simultaneously send an antiparticle to a particle and switch its momentum.
I can visualize it in a S matrix element, but
this is, yeah, I mean, if we were doing S matrix elements, we would just, you could think of this phi hat as sort of maybe creating a K on one side and a perturbative particle on one side. And then we're leaving that K alone, and then we're just flipping whether it's a final soliton state, anti-soliton state, or an initial soliton state. Okay, so yeah.
So what you're doing here with the diagrams and then writing down the amplitude, it's based on the assumption that these diagrams make sense, right? So your first version of the question is that should we consider these processes, and now you are assuming that we can, and then you're proceeding to see.
Yes. Well, yes. I mean, certainly, again, by unitarity, if we had exact control over the QFT, non-perturbative control, then we're obliged to consider those processes. Yeah.
And why is it that this right-hand side is easier to compute than the left-hand side?
Great question. Great question. So the reason, and this is what I'm going to come to, is that on this side here, we have a classical solution, a classical equation with a classical solution that forms the starting point to do quantum field theory around it. Whereas over here, there's no such result known for a classical solution, right? For a particle, a fundamental particle, to pair create. What equation would govern it to pair create a soliton anti-soliton? Okay. That's the reason. So let me kind of expand on that a little bit, but let me rephrase my initial question in one more time. So this is version 3 of that question. What is the leading in G behavior of soliton form factors at? Now this part here is crucial, and this is why this question is still hard, right? We're not getting away with making a hard question an easy question. We need to understand the behavior of these soliton form factors at momentum transfers, PF minus PI. So momentum transfers K, that equals PF minus PI of order the soliton mass. So square root minus space-time invariant k squared greater than or equal to the threshold to create solitons. Because when we analytically continue back to the original picture here of pair creation, we need to have momenta of order the soliton mass in order to pair create. And so we need to understand this form factor as a function of k, the momentum transfer for k is of order the soliton mass. And so let me make some comments about that. So note so PF minus PI, similar to the soliton mass, implies that we're talking, since momentum is gamma and v relativistically, means that we're talking about order 1 velocity transfers. Not just order 1 velocities, order 1 velocity transfer, order 1 changes in velocity for the soliton. Okay, and so in other words, large acceleration. We are giving the soliton a mighty kick with this little perturbative particle. So the point is, I'm only trying to do this to leading order g. So I still have one thing to help me, which is small g. So I can still make approximations in small g. But what I cannot do is make the usual sort of Manton type approximation, the adiabatic approximation that's usually made when we're studying solitons, slowly moving. Okay, slowly varying fields.
Can we again emphasize why you need large acceleration for that?
Because that's equivalent to considering momentum transfers of order the soliton mass.
What do you want that?
And we need to do that if we want to be able to learn anything about the original channel at enough energy to pair create. Right? You have to be above the threshold. Yeah. Okay, so the plan for the rest is basically to set up semiclassical. I'm just going to start calling semiclassical SC computation to let's say towards answering version 3 of this. So let me just make some comments before we go on now. So we could consider small momentum transform, and then we would better recover things that are not classic results. Okay, so in the small momentum transfer limit, the Fourier transform of that matrix element, right, the soliton form factor, it's a classic result going back to, I believe, Goldstone and Chakib. That what it is it's the Fourier transform of the classical solution itself. The Fourier transform of the classical profile that is the classical solution to the equations of motion. So that's what this form factor should reduce to at small momentum transfer. But it's not correct to think of that and look at that function at large k and think that it's describing what we're after. Second comment is that in integrable models, like sine-Gordon, for example, sometimes you can actually compute these form factors exactly, right? Because you have the exact S matrix. And you basically do the optical theorem to get the form factor itself. And so in sine-Gordon theory, this form factor can be computed. And so I want to just talk about, to get a feel for what kind of thing we'd be looking for in a non-integrable model. Okay. So in sine-Gordon, here's the potential, here's the classical soliton solution. And what's been computed is the topological current epsilon mu nu d mu phi, or sorry, d nu phi. So it's just a derivative of the basic field. So we're computing the matrix element of that between two soliton states, Fourier transform. So what does it come out to be? So you've got some kinematical prefactor here because we've got some Lorentz transformation properties. And then you've got a function of theta. Theta is the invariant mass, or the invariant momentum transfer divided by the mass, or twice the mass of the soliton squared. Okay, so theta is defined through this relationship. And in terms of that, this is the function. This is what the function looks like in the G to 0 limit. Okay, the leading semiclassical behavior of this function, but to all orders in K. So there's a prefactor, which is indeed the Fourier transform of the classical profile. So you take this classical solution, you take this derivative, you take the Fourier transform of that. That ends up being a function of the momentum transfer K over little m, the mass parameter that appears in the potential, the mass of the perturbative particles. But then there's this exponential dressing. And up in the exponential, you've got a -1/g². And then you've got a very non-trivial function of theta. So this is those high, these are, you can think of as K over M soliton corrections, dressing this classical result, or, classic result. So what is this function for sine Gordon? So since if you expand it around small momentum transfer, that's K squared equals 0. And so you're actually up at I pi in the complex theta plane. So what you do is you set theta to I pi minus theta tilde, right? And then small momentum transfer is small theta tilde. So I'm going to look at this as a function of theta tilde. So at K equals 0, it's 0. And that's good because e to the 0 is 1, and I get back that the form factor is the Fourier transform. But as you turn on K over M soliton, you get a non-trivial function, and you can even write it down in terms of polylogs. Okay. So what we would be after, the goal would be in phi to the 4 theory, for example. What do we get instead of this?
But doesn't this example already answer your question?
For sine Gordon, sure.
So
Well,
your goal is not to answer the question, I guess, and your goal is to find that phenomenon occurring in other, not exactly soluble systems.
exactly. Is it always going to be of this form?
I see.
Kind of a universality type.
But this surely must give a hint, right? That this is what we expect.
Yes, yeah. And another way to kind of phrase it is, well, okay, is this a consequence of integrability? Or should it really be of this form, even when you don't have an integrable line? Right? Since after all, this is just the leading G behavior, it ought to be possible to recover this without using integrability and with just using good old semiclassical techniques. That's another way to say.
Right. So, and if your question is about the G going to 0 limit, shouldn't we be worried about the classical solution with singular and G?
Yeah, but that's like the usual fact that you do have this e to the -1/g² behavior. That's exactly where that behavior is coming from, because it's like the classical solution squared up here. The classical solution isn't one. So yeah, we are getting a non-analytic behavior around G equals 0, which is famous for for non-perturbative effects in quantum field theory, and we're after that coefficient, right? Yeah, we want to understand that we're not setting G to 0. We're just looking at the leading behavior as G goes to 0. That's okay. So it's, as we're seeing here, it's a very basic question in any QFT with solitons. It's been around since the 1970s, since people first constructed solitons in quantum field theory. And it's an open question. What is this behavior at large K? There's a superficially analogous phenomenon in the standard model, which arises from sphalerons in electroweak theory inducing baryon number violation. Okay, it's kind of an unresolved issue in the standard model. So there's classical field configurations that describe baryon number violating processes. And when the energies in these processes are very small, then you can estimate the probability for this to happen by doing a tunneling calculation. But what's not understood is when the energies are high, what is the right semiclassical approximation to do in order to get the leading estimate for this probability? First failure on induced Barrett number violation. So kind of similar in spirit. So maybe if we can understand this in some more basic model, we can get some insight into something like that.
Okay. I suppose you are not going to mess around with gauge.
Not yet, but that's a long-term goal.
Long-term goal.
Yeah,
And
because
when you do that, I guess then the issues of deep brain physics may come in. I suppose. Is that right?
yeah, there could be some deep brain shenanigans at some point.
Yes, exactly.
But no, the techniques that I'll be using, kind of the basic key input, has been developed for monopoles in Yang-Mills Higgs, so it would be possible. Okay, so let me move on to part 2. And should have been keeping track of time. 26. Okay. FSE is going to be my abbreviation for the Solitons equation, which we'll be meeting here in a bit. So as you might have been guessing, I'm going to work in the simplest possible setting, just to keep things as simple as possible. Models on R11. But as we said, a long-term goal would be to look at other types of solitons. Okay, so what kind of models? So let me start by giving you the classical action. Just a single scalar field. Let's call that be classical for a second. And to give you another example besides Sine-Gordon, the other kind of most canonical example is phi to the 4th theory, where the classical of phi is 1 over g squared times g squared phi squared minus 1/4 m0 squared. And the classical, sorry, that's a CL. Kink is m0 over 2g hyperbolic tangent. M0 over 2 x minus big X. Okay, so this big X is an integration constant right now. That's the position of the kink. Now we want to do quantum field theory, not classical field theory. And in quantum field theory, the classical or bare parameters in the potential are related to the renormalized, finite renormalized ones, they're counterterms. And one of the virtues of this class of models is that there exists a renormalization scheme where G is constant, really constant, doesn't get renormalized. And the only parameter that does get renormalized is the mass. And so what we can do is to describe the counterterms. So the renormalization prescription is that the tadpole for the meson fluctuation, the perturbative fluctuation around the minimum vanishes to hours. In other words, we really are expanding the quantum theory around a vacuum. And so that then induces a bunch of counterterms for the mass. And conveniently, all of those counterterms can be organized as follows. All I need to do is delete this little CL here and delete the little knots on my mass. And then write plus delta V here. And oh, thank you. that would be necessary to get phi to the 4, wouldn't it? Thanks, Chris. Okay. So here these counterterms are originating the relationship between the bare mass. Yeah, so this, let me call its coefficient delta m squared. And the finite renormalized mass. So what happens with the counter terms is they are such that the potential at leading order looks exactly as the classical potential did, but just in terms of rather than the bare mass, the finite renormalized mass. And then there are order g squared suppressed terms here, which include the counter term coefficient, the delta m. And with that, then I just will delete these. Okay, so now we need a basic tool to start to look at those matrix elements, those form factors. So we're going to start with a very general expression for such matrix elements in terms of the Feynman base space PI for matrix elements of local Heisenberg operators. So very generally, if you want to know the matrix element of some Heisenberg operator O hat, which is a function of your basic field phi hat and its conjugate momentum pi hat, and we're just going to imagine a single operator insertion at a single space-time point, Tx. We want to know the matrix elements between two asymptotic states. Well, there's a path integral. It's a phase space path integral over d phi d pi. You've got your initial and final state wave functionals. For example, if we wanted to do the vacuum, these would be Gaussians. And then you've got your action in Hamiltonian form. So e to the is integral dt prime. This is from ti to tf of pi. Oh, and then we got integral dx phi dot, and then we've got minus the Hamiltonian. And the Hamiltonian, it's just the one you think it should be, and it's not that important. But for those of you here, you can see it. It's this one up in the corner. We'll get to the next line in a minute. And then, of course, I have my insertion, my phase space function. Again, this is just inserted at a single space-time point Tx. Okay. So pi is the momentum canonically conjugate to phi. These guys specify the initial and final states, and this is a local insertion. Just very general. Okay. Now, what we want to do is, if we're going to study these matrix elements, these soliton form factors, we have to know how to define these one particle soliton states. Okay, so this goes back to the original works, and this functional integral formulation of it is due to Gervais, Javicki, and Sakino. So the basic idea is that we're going to change variables in phase space from the original pi phi to a capital momentum P, a momentum field curly pi, capital X. So this is where this kink position becomes promoted to a dynamical variable, the collective coordinate, and a field chi. Now, to preserve the degrees of freedom, because we've got these X and P's, these fields, chi and pi, have to satisfy a constraint. And they're constrained to be perpendicular to the zero mode corresponding to motion of the kink. Now that zero mode is actually just the derivative, the x derivative of the classical solution. Now what does this change of variables actually look like? So let me write it down for you. Phi of tx in terms of the new fields is the classical background, which is a function of x minus big X, but now we're thinking of big X as a dynamical variable, so it's a function of time. And then chi is the fluctuation around that background. So it's a function of t, and also we center it on the kink. So that seems pretty reasonable. The expression for pi might not seem so reasonable to you. Let me write it out. First, there's a fraction. There's big T, P, which is canonically conjugate to X. And Now I'm writing some single bracket thing with my new curly pi and chi prime. And I'm going to divide by the classical soliton mass plus another one of these brackets with the zero mode against chi prime. And I'll explain the notation in a second. This multiplies the zero. So here there's got to be dx by naught. And that is a function also of little x minus big X of t. And that is just the first term, like kind of the analog of this. And then we have to add to that the fluctuation, which is the curly pi. It's a function of t and little x minus big X. Okay, let me explain the notation here. Where, okay, the single bracket, here we go, fg, this means the integral over space, but it's the integral with respect to the centered coordinate. So that's going to be called rho of your product of your two functions. Where here rho is little x minus big X. M naught is the classical soliton mass. So in terms of this notation, that's just the inner product of phi 0 prime with itself, turns out. And then I'm using a notation now where dots are going to be time derivatives holding rho fixed, and primes are rho derivatives. Okay. So this seems reasonable. Where in the world did this come from? Notice it's a non-local transformation with respect to space, but it's local in time. This form is completely determined from the condition that you have this for the coordinate and that you want this transformation to be canonical on phase space. So that the Liouville measure is preserved in the path integral, and so that the symplectic form up top, like the pi phi dot, transforms in the nicest possible way. Px dot plus new curly pi chi dot. So one more.
A simple way to write the condition you're preserving.
Yes. Another way to say it is that if we take the Poisson brackets of the new fields with
the phi and pi.
Yeah, the original fields.
Yes.
Then they're gonna be preserved if we assume standard Poisson brackets for the new fields. And that's a slight lie because there's a constraint. So actually you have to construct Dirac brackets for the new chi and pi. But the statement is that if chi and curly pi satisfy those Dirac brackets that follow from the constraint, and x and p are canonically conjugate, so their Poisson bracket is 1, then the Poisson brackets of phi with phi will be 0 when you use them on the right hand side. Phi with pi will be delta x minus y, and pi with pi will be 0. And those conditions pretty much uniquely nail you down to this. It's a pretty cool calculation. It's fun to do. But yeah, it comes out. One little technical thing, it just is more convenient after doing this to make one more transformation. And this one's a trivial one compared to that one. So instead of using curly pi and chi as my fields, I'm going to use curly pi and curly phi. And the relationship is simply that pi didn't change. And phi, curly phi of t rho is just the sum. So phi naught of rho plus chi of t rho.
And what is the constraint?
I didn't. Yeah. So the constraint is that, for example, the integral of chi against the 0 mode. 0, and similarly for pi.
It's not really an algebraic constraints that you have in mind.
No.
So
So
what does this figure in Dirac formulas, am I wonder?
Oh, you can still do the direct formalism. That's not a problem.
Even though this is an integral constant.
Yeah, it's okay.
Really?
Yeah, you're just doing variational calculus. You can do it. Yeah, I can explain it in more detail, but I think it would be something that would be better after the talk. Yeah.
So you're basically creating two functions of two variables or two functions of one variable each, right?
Yeah, but yeah,
two constraint ones.
yeah. Remember that x and the p are just functions of time. So it's what. So see what this is doing. Dx phi naught is one of the eigenmodes of a fluctuation operator. It's the zero mode.
Right.
And so what we're doing is we're just doing an eigenmode expansion of the new fields, but then we're saying I don't want the coefficient of the zero mode. I'm going to trash it, set it to 0 by these constraints, and those 2 degrees of freedom are being replaced with x and p. And the reason we have to do that is because of their zero modes. If we didn't do it, the propagator wouldn't work. So we have to treat that 0 mode degree of freedom exactly, non-linearly. That's what the collective coordinates are. Other questions so far? So now that we have these new variables, I can finally tell you how to define Soliton states. Okay. So what are Soliton states? How do we define them in the QFT? Now it's pretty simple. So one particle state, Soliton state, is going to be defined as follows. So it's an eigenstate of that capital P, and then it's tensored with a ground state in the curly phi sector. So this is the ground state. Kind of like an analog of a vacuum in the perturbative sector, except it's not a vacuum because we have a soliton. And this ground state will depend on P if the momentum of the soliton is not 0. So you'll see that in a second. This is the ground state of the phi sector. And this is just a standard quantum mechanical waveform, plane wave. So returning now to look at our form factor or our matrix element, for soliton states specifically, we can all right, canonical transformation. So I don't have to worry about annoying Jacobians here. The measure is just the canonical Liouville measure. But now we have x and p, and from my initial and final state wave function, we have these plane wave factors now. And this is just basically setting up the proper boundary conditions on your path integral over x and p. But then we have the field theory path integral over these d pi, d curly pi, and d curly phi. And then we have the corresponding ground state wave functionals here. So this would be f. And then we have our action, e to the I f in Hamiltonian form, but in terms of the new variables now. And again, because it's canonical, I just get p x dot plus integral over d rho pi psi dot, and then I have to subtract off the Hamiltonian expressed in the new variables. And that's what I've put here. This is what you get for the Hamiltonian when you plug in that change of variables. O is now supposed to be, it's still the same insertion we had, but now we should plug in the change of variables and express O in terms of the new variables. So I'm just going to kind of denote that like that. Seems like I made a very formal thing, much even worse and more nasty. But now we're in a position, so this is exact, but you can't do much with it exactly. Now we're in a position to make a semiclassical approximation. Okay. So this whole field theory path integral with the insertion we're going to make a stationary phase approximation. But here's the key. In the presence, so notice that the Hamiltonian does depend on this big P of t, right? Our dynamic, one of our dynamical variables. So we got to make the stationary phase approximation for pi and phi in the presence of a general P of t. So from the point of view of pi and phi, it's like a background view. And why do we have to do that? So at this point, if there are two assumptions that are often made, or one additional assumption besides G is small, which is that P is small and constant, or at least that P is constant. Now, why would that ever be a good assumption? Well, if there were no insertion here, right? If we were just studying the transition amplitude, one thing you'll note about this new Hamiltonian is that it does not depend on capital X at all. And that's a reflection of the underlying translation invariance of the theory, okay? So without the insertion, the equation of motion would say that P is constant, okay? But with the insertion, we can't assume that. If you assume P is constant and small, then the leading saddle point expression for this just gives you your plus P squared over 2m, all right, your Hamiltonian for a non-relativistic particle. If you assume your P is constant but not necessarily small, this was done by Gervais, Javicki, Sakita, they showed that this thing has a non-trivial saddle point. They found that solution. They evaluated the Hamiltonian on that solution. And when all the dust settled, it gave them square root P squared plus m squared, the relativistic energy of a particle momentum P. What we did is find the saddle point equation for a general P of t. And that's what leads to the forced Soliton equation. So let me write that down. So let me just keep going with this equality. And then I have to define a couple of things that I'm going to introduce. So carrying out this stationary phase approximation, then this whole thing collapses down to what looks like a quantum mechanics. And let me just shorten this plane wave exponentials by just putting some boundary conditions here. And then what do we have? We have exponential of x dot minus some h semiclassical, which is a functional of p only. And then we have our insertion, a semiclassical insertion, which is a functional of p and little x minus big X. And then we have 1 plus order G. Correction. So I have to tell you what HSC and OSC are. But OSC is only a function of these two things because what we're going to do is we're going to evaluate this on a solution. And that solution will be a function of P. And it depends on little x minus big X only because of the original form of the field transformations. When you express pi and phi, the original pi and phi, in terms of the new variables, the big X only appears in this combination, little x minus big X. Okay, so what are these two things? So HSC is the field theory H evaluated on a solution, which I'm going to call curly pi bar, curly phi bar. I don't have to tell you what that is, plus the one loop correction. Won't say much about that. So this is a solution to equations of motion. Follow for curly pi and curly phi from that Hamiltonian with that non-local term showing up first there. And when you eliminate pi and you get a second order equation for phi, that's the force soliton equation. So here's what it looks like. D by dt minus beta. Beta is a velocity, but it's a functional of the solution, which I have to tell you. So it looks kind of like a plane or a wave equation. And then we've got our derivative of our potential. Evaluated on the solution. And then we've got a forcing term, which explicitly is proportional to the time derivative of p. So p dot. It also has some normalization involving the solution. So remember, these are representing integrals over rho. So this is what's called an integrodifferential equation. Well, it's derivatives of the function you're trying to solve for, but also integrals over that function you're trying to solve for. So it's non-local in space, but it is local in time. Let me make some comments about this equation. Do we know any solutions? Only if p is constant. So we think that for given initial conditions, there is a unique solution, but analytically constructing it seems impossible. Comments? Okay. If p dot is 0, so we are in the case of constant p, and I can write down the solution for you. This is the one that Gervais, and Sapina found. It is the original classical profile, but boosted. Don't worry about rho naught. That's the constant that's fixed by the constraint. But here, gamma is the Lorentz contraction, or in terms of the soliton momentum, 1 plus big P squared over soliton mass squared. And in this case, when you evaluate the Hamiltonian on that solution, you can get, like I said, the square root P squared plus m naught. That's the tree level. That one loop thing that I said I wasn't really going to talk about gives you the first correction to this, which comes from the one loop correction to the soliton mass itself. Where delta m is the one loop correction. Another nice fact is that this force soliton equation preserves the constraint under time evolution. What do I mean by that? As long as you set up your initial conditions to satisfy the constraint, then the time dependent solution will satisfy it for all times automatically. Right? So the equation, the evolution determined by the equation, stays orthogonal to those 0 modes. That's hard to see in the form that I wrote this equation here, but if you write it in Hamiltonian form, it becomes clear. What you should do, how you should think about solutions to this equation, well, how I think about them. I think of a solution to this equation as a nonlinear soliton analog the linear feature, potentials and electromagnetism, which you might recall are the form that the potentials take for a charge particle that you accelerate along an arbitrarily specified trajectory. So this solution is, remember, P of t is being treated as a background. So you give me a P of t with some profile, some time dependence. This equation then describes what the soliton and all of its radiation it produces looks like as its position is being accelerated along that trajectory. Okay, real quick, OSC is just what I was saying. It's the original O, plug in the change of variables to the soliton sector, and then evaluate it on this solution. Okay. So I've got about 5 minutes. Yeah, okay. So I'm just going to say a few words about part 3, because this is where we get into work in progress pretty much. But what I've erased there now, right, we still had, in order to get at the matrix element we were really trying to get to, we still had this quantum mechanics path integral to do over x and p. Okay. And remember, let me denote that thing now, this. So we're interested now in the matrix element of this semiclassical O between the P eigenstates, where the Hamiltonian in this quantum mechanics, it's not really quantum mechanical Hamiltonian, because it's a very non-trivial functional of P, right? And it'll have, if you were to do an adiabatic expansion with it, it would have an infinite tower of higher time derivatives of P. Right? So you think of it like an effective Hamiltonian that we got by integrating out degrees of freedom. So the cool thing though is the trick that lets you make some progress is to think about this in terms of generating this insertion by taking derivatives of a generating function in this quantum mechanics. So I introduced two sources, K conjugate to P and J conjugate to, or sorry, F conjugate to X. And I take my phase-space function and I make it a functional of those derivatives, and I let this thing act on this guy. So I've got my E x dot minus HSC of P, and now I include two source terms, minus KP and minus little x minus big X F. And now you look at this and you don't know a lot about this HSC of P. But the amazing thing about the one redeeming feature about this whole thing is that HSC does not depend on big X at all. So if you look at the big X dependence here, it only shows up in the Px dot term and in my source term. I can integrate out big X. It's a plane with it, right? I do the integral, I get a delta functional. The delta functional, what does it do? It says that P dot integrate by parts has to equal your force. In other words, it enforces Newton's second law for the soliton. Where this external force F, right? That is literally the force, right? That is driving the soliton. Okay. Now I'm just using it as a tool. Eventually, once I take all these derivatives, I'm going to set K and F to 0. Okay. But now you've got this delta function. You can use it to integrate over P. And so you can carry out this path integral, and integrating it over P sets P to the solution with that force. So I call that P bar of T prime equals Pi plus the integral from 0 to T prime T double prime F of T double. So P then becomes a functional of the force. And now your task, give me the O so that I actually know what functional derivatives I have to take and take them. And we're making progress with that too. But that is where we're really at work in progress. And what I'll just say is that we get a result that looks so close in form to something like this. But unfortunately, instead of this thing being a function of the Lorentz invariant k squared, it seems like we're getting something like this, but in terms of the spatial k. In other words, our result doesn't seem to have the right Lorentz transformation properties. So I'm not sure what we're missing yet. Like I said, it's work in progress, but that's one of the things we're thinking about right now. And hopefully we'll be able to get that resolved because it looks like it's getting there. This would then, and then what the S would be, or what it is in that case, is it's basically this time integral of this HSC evaluated on a specific solution with a specific force. So what happens is you get localized on a specific force, which is a delta function force. And so the P bar of T that is relevant, that ends up being relevant, is this one, where the impulse happens at the T of the insertion. And the jump is the K. So find the solution to the force soliton equation with this specific P of T. Now you've got a function of K in principle. Take that, stick it into the Hamiltonian, do the time integral. That is what's going to give rise to this S as a function of K. That's the idea. One other thing that I'm doing with Doug Rutledge and a student at Penn State Fayette is we're trying to look for numerical solutions to the force soliton equation. And so I had a little video, which I think I forgot to load onto the computer. So I can show anybody who's interested later since we're out of time. Anyway, and right now it breaks down numerically. So it's also in the very early stages. But it looks promising. So I'll stop here. Yeah, thanks.
Thank you very much. So that was awesome. Do we have any questions? Perhaps first of the people who are here, and while there's some people on Zoom can think about it, perhaps raise your hand. So
yeah, Andy, so I think in the beginning you made this assumption that in the decay diagram, the particle is going and it's breaking into soliton and soliton. And I think it's crucial to make the assumption that the change in momentum took it to be proportional to n. Now, I mean, is this very specific to a soliton anti-soliton diagram, or I mean, this looks to me a very general.
No, yeah,
process.
yeah. Well, except that I want to consider those to be soliton. Like I'm specifically interested in the process where those are soliton states. So perturbative particle straight pair creating solitons. Now you can consider that off-shell amplitude with the soliton states in the perturbative particle for any k you want. You don't have to take momentum transfers of order the soliton mass, just thinking of it as an off-shell amplitude. But in order to access what the probability would be, or more precisely, what a leading contribution would be for pair creation, that amplitude won't contribute to this, like, when you do like an optical type, that amplitude won't contribute to this until you get above the pair creation threshold. So if you're interested in applying that amplitude to understand this, that's why you need to consider K's that large. But you could just study the amplitude more generally, which is what I was showing you with sine Gordon, the exact answer for any K.
Right. So I mean, if I apply the same technique for any other theoretical process, then I should be able to do some probability expansion.
Yeah.
And,
yeah. The reason that it's so much it's difficult here is precisely because we're dealing with solitons, and the only way that we know how to define soliton states in a QFT is through this process that I described to you in general. Yeah, we can't. There's no creation operator that we can just write down and it pops out a soliton. Yeah.
Okay, great. Are there any other questions? No?
So if one consider the crossing symmetry of CFT, the usual thing, do you think that one can gain some more knowledge about that?
Yeah, but CFTs don't usually have solitons. That's the problem, because usually a soliton, has to have you have to have in order to have a topological charge, oftentimes anyway, you have to have a set of discrete vacua, and then there has to be a gap from the vacuum to the spectrum of perturbative particles. So for example, with monopoles and Yang-Mills Higgs, it's the Higgs Vev, right, that gives you that mass scale. And then the mass of the soliton, the monopole, goes like the Higgs Vev over G squared. Mass of the kink goes like the little m over G squared. So and a counterexample to that, a very interesting one, is instanton solitons in 5-dimensional gauge theory, where you basically take an instanton configuration in 40 gauge theory, and you just, now you're in 5D, you've got time, and so it's just a static spatial field configuration. And then because it's just Yang-Mills, except there it's the coupling itself which is dimensionful, so it's not, I guess, a CFT even so. So yeah, it would be nice. But, yeah.
Okay, very good. So I think there are no further questions from our Zoom audience. So then I will stop the recording. And